All right, we got our notes out. We should have our ACTS packets out. Once again, ladies and gentlemen, today we are going to continue on with our molecular geometry. So our learning target, same as yesterday, determine which type of model is the best representation of the compounds. So we're still in that process. And today's success criteria, I can identify the ACTS method for molecular geometry. Just at the end of yesterday, we started talking about the ACTS method. And the second thing is to actually determine the molecular geometry and represent.
Mr. Braun?
Yeah.
Sorry for the interruption. Do you have Brianna?
So we need to be able to represent compounds using a perspective drawing, okay? And we're going to call those perspective drawings Fisher projections. So I can represent compounds using a Fisher projection. Now, when we finished off yesterday, we were talking about the Fisher projections. We said that bonds in the plane of the paper are shown as lines that, I believe on the video, we called hashes. No, we called these dashes. These were dashes, okay? Triangles or wedges are bonds that are projecting to the front of the plane, and the hashes here at the bottom are the bonds that are projecting behind the plane. So as I'm looking at this, these dashes are on the plane of the paper. These are projecting forward from the paper. These are projected back from the paper. So those are the three ways that we are going to represent bonds, and you're going to see we're also going to represent unshared pair with those. Okay? So we're going to just start off by working a couple. I'm going to go through methane here. We finished this up yesterday, but we're going to do it again. So I'm going to look here and say, all right, I've got methane right there. There is the bonding of my methane, and when I ax it, okay, A represents the central atom, which is carbon. X represents the number of shared domains, bonding domains. And E represents the number of unshared pair, the non-bonding domains. So when I ax this particular one, I get AX4 E0. So once again, when I check on my AX packet, okay, what is AX4 E0? Go ahead and find that. The ones I like to use to find that, these folks are right here. Okay, these ones, where I'm looking for AX4E0. When I find that, you should find that your molecular geometry is tetrahedral. Correct? Now, what I'm going to do here real quick. Okay, let me, because we're right here, we'll get the ax. I need to pull up that ax. So let me get my taskbar here. Here's my ax packet. You can't see it very easily, so let me blow it up a bit. When I came here, right here is my A. Right here is my AX4E0, which tells me that that is tetrahedral. So my molecular geometry is tetrahedral. Now, I need to go back and I need to do that Fisher projection. So I'm going to go back on, I don't want to do that. I still don't want to do that. Let me go up here. I'm going to go back up on my diagram until I find tetrahedral. Okay? Where is my tetrahedral? There it is. Let me get that off of here. Now here is my tetrahedral. So when I'm doing my Fisher projection for methane, I'm looking at that right there because that is tetrahedral. So when I come back to my PowerPoint here, I can see that I am going to have my X drawing for tetrahedral. Tells me that my A is here. I have a dash line for that X. I have a dash for that X. I have my hashes for an X here, and then I have a wedge right here, okay, with an X. Now, all I simply do, that's the drawing I'm looking at. So all I simply do is where I have these X's and the A, I replace them because the A is my central carbon. Okay, the X's all are H. So as I am looking at this, I can see that these two bonds are on the plane of the paper. This bond with the hydrogen is projecting out towards me. This bond with the hydrogen and those hashes is projecting back into the wall. So that is what I'm seeing there. So my correct Fisher drawing, or my correct Fisher projection for methane is that whole guy right there. Now let's continue on. All right, we're going to continue on with water. So as I'm looking at water and I'm axing it, I see two bonding domains, I see two unshared pairs. So I see two bonding, I see two non-bonding. So as I look at this, I'm looking for AX2, E2. AX2, E2 in my packet. When I come back, let me put my pen down, I come back here to my Axe packet. Okay, I come back here to my Axe packet. I'm going to get that circle off of there. I'm going to get that line off of there. I'm coming down. Where is AX2, E2? Right here is bent. Now remember, the one right above it is also bent. I have two bents, and the difference is this E2 and an E1. So I'm doing the bent here that is AX2, E2. So when I go back to my other projection one, I need to make sure that I have two unshared pair, not one unshared pair. So as I get this stuff off of there and I come back, okay, here's a bent and here's a bent. Which one of those do I want to use? I want to use the one that has two unshared pair, correct? So I am going to use that one right there. So as I go back to my PowerPoint show here, I've got a Fisher projection to make. As I'm looking at my Fisher projection for bent with two, I have hashes to an E, I have a wedge to an E, and then I have dashes to two X's. So that is the one I'm looking at in my Fisher projection. I need to go in. I know that my X's for this particular one is hydrogen. I know that my A is oxygen. And I know that these E's up here, those E's are unshared pair of electron. So I'm just going to represent those E's as an unshared pair as so. The two dots, the two unshared electrons. So, as I look, these two bonds are on the plane. This unshared pair is projecting back towards the wall. This unshared pair is projecting out towards us, out towards me. So my Fisher projection right there for water is so. Get those arrows. So there's my Fisher projection for water. Ammonia. Ammonia is another common one that we see. We're going to work. When I ax ammonia, I see AX3, AX3, E1. AX3, E1. Head back to my ax packet. A X3 E1. Come down to this part of it. AX3 E1. Here I am. AX3 E1 trigonal pyramidal. So my molecular geometry is trigonal pyramidal. I come back up to find trigonal. There's trigonal planar, trigonal pyramid. It says trigonal pyramid, not pyramidal. This is the one I'm looking for, right there. Trigonal pyramidal. So I come back to my PowerPoint, and I say, okay, I have, for my Fisher projection, I have A, I have E, and I have X. I have a wedge with an X, and I have hashes with an X. Once again, I'm going to replace A. I'm going to replace A in this particular one with my central atom, which is nitrogen. This E up here is an unshared pair, and these X's are all hydrogens. So, ladies and gentlemen, I have just created the Fisher projection for ammonia. Now this last one is a little bit tougher, because I look at this and I say, okay, here's selenium and here is 6 F's. So I have selenium hexafluoride. You don't know how to name that quite yet, but that's what it is. So what I would do if I were you, there's a couple of things that we can do if we get something like this. Well, number one, we can always say, okay, what is, and here's what I Googled. I Googled, what is the Lewis structure of selenium hexachloride? You could have just put SeCl, or excuse me, SeF6. I don't know why I looked up hexachloride. It should have been hexafluoride. But you can see right there is a Lewis dot structure. Now, obviously, this is one where we're talking expanded valence, because we don't just have 8 valence electrons around that selenium. Okay, we're pulling in different orbitals. not just the S's and the P's that we are used to. So we're pulling in these different orbitals for that. I'm going to come back down here and pull up this diagram here. Now, what I'm looking at, out on the side here, okay, out on the side here, I can see that we have different examples of this particular type of an element. Now, if I have selenium, okay, once again, I have selenium SeF6. All right? So, I'm looking at my periodic table and I say, okay, is there anything? Selenium, sulfur, oxygen, tellurium. That's all the oxygen family. Okay? Is there anything? Is there an OF6? Is there an SF6? Is there a TeF6? Well, as I go down, well, lo and behold, ladies and gentlemen, right here is SF6. Sulfur is in the same family as selenium, right? Would you expect that SeF6 would act similar to SF6? Absolutely, they're in the same family, selenium and sulfur. Okay, so I would expect, yes, those are going to act like each other. So even if I didn't have the Lewis structure, okay, I could look at these and say, okay, this is going to be similar. Now, when I go back to my PowerPoint, I want you just to remember the AX6E0, because when I come back to my PowerPoint here and I bring up, here is my Lewis structure for that, and I look at the selenium, and I see that there are 1, 2, 3, 4, 5, 6 bonding and 0 non-bonding. So I get AX6E0, which just told me that that was octahedral, right? Told me it was octahedral. So as I am drawing my Fisher projection for octahedral, I see that I have an A in the middle. I have an X up top. I have an X down at the bottom. I have a wedge with an X. I have another wedge with an X. And then I have hashes with the X's. So there's my Fisher projection that I need to draw. So when I do so, I'm going to start off getting that A out of there. And I'm going to put SE in place of that A. And then where I have all these X's, I'm going to put fluorines. Ooh, ooh. Where I have all these X's, I'm going to put fluorines. So there I have my Fisher projection for selenium hexafluoride. Yeah.
So, selenium should have more than 3 bonds. Why is that?
I just told you, expanded valence. You don't need to know that. You'll learn that if you take AP chemistry. What you're having is, I talked about the S and the P orbitals that we're dealing with. These are bringing in some d orbitals too. Okay? So some bonding's occurring with d orbitals. So as I look at this once again, okay, I'm just following my AX packet and I'm counting unshared pair and shared pair, which we call bonding and non-bonding domains.